All right, so our next problem we have, a researcher is interested in whether a new reading technique influences the reading ability of elementary school teachers. The researcher knows that the average reading ability among the population for third graders is a mean of 3 with a standard deviation of 1. If the researcher administers the new reading technique to a third grader and who substantially scores a 4, can we conclude that the new reading technique works or doesn't work? Basically, we're doing that rejecting the null or not rejecting the null. We've kind of gone over this a little bit more. Now remember, in order for us to say that this probably has a technique, we want a z-score of greater than 2. And that's just kind of be our realm on this particular one that we think it might have an influence. So when we do our z-score, again, remember it's x minus mu over the standard deviation. So this is going to be 4 minus 3 divided by 1, or 1 divided by 1, which is 1. 1 standard deviation above the mean is not enough to say that this particular technique has an effect on the reading comprehension of a third grader. So if we look at our options here, it's definitely does not have an influence. It doesn't decrease the reading ability, and we can determine this, and that the determination we can make is that this does not have an influence on their reading ability. Okay, again, if we're doing this, we want that value to be a little higher, probably closer to 2 for right now, when we're not doing all of our hypothesis testing that we've already done in previous chapters. Okay, so a sample with m equal to 85, or a mean of 85 and a standard deviation of 12, is transformed into a z-score. After the transformation, what are the values and the mean and the standard deviation of the sample of z-scores? So again, the idea here is that for z-scores, our mean is always 0 and our standard deviation is always 1. That's the standard mean and standard deviation for this. So that would be this guy right here. Every time we talk about z-scores, our mean is 0, our standard deviation is 1. So a set of scores ranges from a low of 25 to a high of 33 and has a mean of 29. Which of the following is most likely the standard deviation for these scores? So the way you've got to think about this is think about your mean is your middle score, right? And you have a low score here at 25, you have a high score here at 30. So if you think about the distance from here to here, that is 4 points. And if I think about the distance from here to here, this is also 4 points. So if I think about it, I can't have a standard deviation that's 10 points when the difference between my mean and my low value is only 4. So that can't be right. 2 could probably work. 34 is not going to work. Again, that's way too high. And 5, that's also bigger. So my only option here is 2, because all of the other values are larger than my difference between the mean and my lowest value. The same thing with my mean and the highest value. Since they're only 4 points, my standard deviation needs to be smaller than that number 4. Oops, I'm sorry. All right, then which of the following statements are a unique advantage of the interquartile range for a measure of variability? And again, we're going to select all that are correct. So it says the interquartile range can be used for data measured with a ratio scale of measurement. Okay, the interquartile range is less influenced by the range of extreme values. The interquartile range can be utilized in open-ended distributions, and the interquartile range can be used for data measured with an ordinal scale of measurement. So guys, the answer to this one is the last 3. These are all true, especially this middle one, or the second one here. That was one of the big ones there. It was less influenced by the range of extreme values. That's one of the reasons we like the IQR over just the range, because it's a little bit more understanding of what is happening there. Okay, and then our last question, we are going to calculate the variance and standard deviation again for sample data. So we're going to start off by creating our chart, and we're going to do our x's and our x squared here. And we're going to do our x's, so 1, 0, 3, 1, 2, 4, 0, and 5. I'm going to add all of that up. That's going to give us 16. I'm going to take and square each one of these, so 1, 0, 9, 1, 4, 16, 0, and 25. If we add all that up, that's going to give us 56. So remember, our sum of squares formula is the sum of our x's squared minus the sum of our x's, and then we square them, divided by n. So the sum of our x's squared is going to be 56 minus 16 squared divided by the number of data points, which in this case is 8. That is going to be 56 minus 32, or 24. So now we're going to find our s squared. Remember, this is our sum of our s's over n minus 1. So this will be 24 over 8 minus 1. So 24 divided by 7, and that's going to give us 3.43. There is our variance. And then remember, all we do for our standard deviation is take the square root of 3.43. That's going to give us 1.85, and there's our standard deviation. So again, just making sure you remember those formulas for sum of squares. And then the only difference between sample data and population data is that denominator when we're doing our variance. So for population, it's just n. For sample, we do n minus 1. If there's something I didn't go over that you don't understand on exam 2, just send me an email and I will look at giving you another video with some more questions.